Optimization problem, maximum minimum problems. Example 1. A rocket is fired into the air and its height is in meter is in any given time t can be calculated using the formula h of t equal to 1600 plus 196t minus 4.9t squared. Find the maximum height of the rocket and the time at which it occurs. So we want the maximum height. Okay, so we know we need an equation for the height, which we already do. And to find the maximum minimum point, we need to take the derivative and set it equal to 0. So we take the equation given to us, find dH dt, first things first step. Okay, then we take that derivative equal to 0, so t equal to 20. All right, now, so we know at 20 equal to 20, we have either maximum or minimum point. So let's use a second derivative to verify, make sure that is the 20 is the maximum height we're looking for. When you take the second derivative of the same equation, you get negative 9.8. Now, since the second derivative is negative, so we know it's a concave down. If you have a concave down, then therefore 20 must be the maximum point. So t equal to 20 when you have achieved the maximum point, and the height at that point, you simply plug in 20 back into the equation, then you get 3,560. So the rocket maximum height is 3,560 meters at time equal to 20. Example 2. Max wants to make a box with no lid from a rectangular sheet of the cardboard board that is 18 inches by 24 inches. The box is to be made by cutting a square of side x from each corner of the sheet and folding up the sides. Find the value of the x that maximizes the volume of the box. So for this type of question, okay, anything geometry, it's always good to draw a picture, right? So here's what a picture look like. So you have a metal sheet. Okay, you have a sheet here that's 24 by 18. You could just cut out this corner here. Okay, so we want to know these square corners. We want to know what's the dimension of these the x here, the side of these corners. So you will achieve the maximum volume. You want the box to be maximum volume. So since we want to maximize the volume, so what we need is we want to take the derivative of the volume function. So we need to come up with the volume first. We need to find out a way to describe the volume of this box. Like, so if you look at this picture right here, volume is what? Width times length times height. So if you fold this box up, the width of this box will be 18 minus 2x, because you have 1x here and you have 1x here. And same thing with the length. The length total is 24, but minus 1x on the side, and then 2x's on both sides. I'm sorry, 1x on each side, so you have 2x's. Then when you fold this up, the x will be now the height, right? The depth of the box. So then the equation of the volume will be the product of these three things, right? So x times 18 minus 2x times 24 minus 2x. So once we FOIL that out, okay, when you multiply it out, there show our equation for the volume. Then to maximize the volume, we simply take the derivative. And once we take the derivative, we set it equal to 0, and we solve for it. Here's your algebra. We'll go ahead and use the quadratic formula. Negative b plus minus b squared minus 4ac over 2a. Then you get 7 plus minus radical 13. If we evaluate this without calculator, we find out one is 10.6, the other is 3.4. But if you look at the original picture real quick, 10.6 is not logical. Because if you look, just look on the width here. You cannot, x couldn't be 10 point, couldn't be, 10.6. If x is 10.6 on this side and that side, that together already over 18. So we know this 10.6 is not a logical choice. So the only choice is what? 3.4. Now, to just verify the answer is 3.4. But to verify it, okay, we can use a second derivative to find out. Our second derivative is 24x minus 168. Take our answer, plug it into the second derivative equation for x, then they will kind of confirm our answer for us. It turned out to be a negative number. That's what we want, because a negative number means concave down. If it's concave down, then 3.4 must be a maximizing point. All right, let's do another example. Example 3. A manufacturer company has determined that the total cost of producing an item can be determined by the equation C equal to ax squared minus 176x plus 1,800. where X is the number of units that the company makes. How many units should the company manufacture in order to minimize? We want a minimum point, minimizing the cost. So they already give you the cost function. So that's kind of nice. So all you have to do is take the derivative of that and then set it equal to zero, right? That's always is always what you try to minimize or maximize, and this is cost. So whatever that function is, you take the derivative, you set it equal to zero, and you solve. Once you find out x equal to 11, and once again, all we do is what? We take the second derivative. And second derivative turned out to be 16. That means concave up, and therefore, x equal to 11 must be the minimum point. So the answer is the company should make 11 of this item to minimize the cost. Okay, so let's look at the next example, example 4. So a rectangle is to be inscribed in a semicircle with a radius 4. With one side of a semicircle is the diameter, okay, and what is the largest area this rectangle can have? So again, what we want to do is draw a picture here. So here's we have a rectangle, this red rectangle here inscribed inside a semicircle. And we know the radius of the semicircle is 4. And we want to know what is the largest area possible, right? So we need an area function, right? We need to write an equation for the area to describe this red rectangle here. So all right, so we're gonna let this so we don't know how far this is going to go out. Okay, so we're going to say this length right here. So in other words, half, right? Half of rectangle, like say this side here is x. If this is x, then this point right here got to be xy. Okay, so then what is y? We know y must equal to the half of this equation here. They gave it to us. They provided y equal to the square root of 60 minus x squared. Okay, now the reason you said, well, how do you get this? Because hopefully you remember that equation of a circle is x squared plus y squared equal to r squared. So since we know r is 4, so that's 16. And when we solve for y, so y equal to square root of 60 minus x squared. So this point right here, the coordinate is x, and then square root of 60 minus x squared, because that's what y is. Okay, so now if you look at this equation now, so you have this, so the rectangle is what? Length times width. So the length is actually 2x, right? Because you have one x here and you have the other x on the other side. So you have 2x's times this y here. Okay, so that's the hardest part, to find out this equation. All right, so because the minute you find out that equation, now we know the procedure. All we have to do, if you want to maximize this area, you just need to take the derivative, set it equal to 0, and solve. So, all right, finally, we got an area of this rectangle is 2x parentheses 16 minus x squared is x times y, length times width, right? Okay, so take the derivative of this. Okay, here we go. So, when you now remember this part, you can think of it as 16 minus x squared to the 1 half power. If you take the derivative of this, is 1 half 16 minus x squared to the negative 1 half power, and then apply chain rule of negative 2x. That's why I got this number here. Okay, so that's where this is. So it's so using product rule, so you get 2, okay, times radical 60 minus x squared plus 2x times derivative of 60 minus x squared square root. So here it is. Then we just need to simplify, clean it up a little bit. Okay, we just multiply this out. Then we solve. Okay, so this equal to 0. Now, right now, we just like pretty much algebra, right? So I'm going to move this to the other side, and I'm going to do cross multiply. When I do cross multiply, I end up with the quadratic equation. So we know how to solve quadratic equation, right? When we do distributive property, okay, and then we combine like terms and move everything else, then we got x squared equal to a. So x is going to be plus minus square root of a. Now we know x cannot be negative radical a because it's a length, right? Length of a rectangle, half the rectangle at least. You cannot have a negative number. So radical a is our only logical choice. All right, so when we take the second derivative, okay, and then we plug in our radical a, we find out that it's what it's going to be a concave down. So therefore, you have a maximum point. Okay, but again, now do you always have to like say second derivative is not easy for this question? It's not impossible, but it is quite work. Now, the question is, do you need to take a second derivative to get the point? Well, it's this. You did find the answer already. It's just second derivative serve as a double check, right? To check your answer. Okay, to make sure if you want a maximum point, you need looking for second derivative that's negative because concave down and vice versa. Okay, so yeah, so second derivative. So here we go. So the best probable x to maximize a rectangle is when x equal to radical a. And since y equal to, remember in the beginning we say square root of 16 minus x squared, if we plug in x, right, then so you'll find the y. Okay, so the larger possible area for the rectangle is length times width. Okay, so in this case is 16. Right, so here's another example of the geometry. Okay, a rectangular field bounded on one side by a building is to be fenced in on the other three sides. If 3,000 feet of a fence is to be used, find the dimension of the largest field that can be fenced. Okay, so all right, so basically you have a building here, then you try to fence this in, right? Okay, so we're gonna call this side x, and this is a longer side here. It looks like longer side, at least y, and then here's the x again, right? Okay, so what's the area of this? Area is what? X times y, right? Area equal to x times y. Okay. Now, so and so what we want to do is we want to take the because what do we want? We want the largest field. So we want to we'll take the derivative of this. Okay. The problem is you have like three variables here. You want area, but you have x and y. So what we need to do, we need to do substitution here. So another relationship in this picture here is we know that 2x, so 1x here, 1x here, and plus is y. So you add up all the fences equal to 3,000 because they tell you that 3,000 feet of fence total. So if you have this equation, we can solve for y first. So take the fence equation, the bottom equation here, y equal to 3,000 minus 2x. Then we take this equation, plug into the first one. So area equal to x times, instead of times y, times 3,000 minus 2x. So there's your equation now. So the equation for this area right here, you try to maximize, is area equal to 3,000x minus 2x squared. Now, when you take the derivative of that is 3,000 minus 4x, set it equal to 0, and you can solve. Again, x equal to 750. To confirm that, we can take the second derivative, find out it's concave down, so this must be a maximum point. Okay, then they want to find out, well, what's the dimension of it? Well, we know x is 750, then y is 3,000 minus 2x. Plug in x 750, you get 1,500. So the answer, what dimension do you would you use those 3,000 square feet of I'm sorry 3,000 feet of fence is 750 feet by 1,500 feet.